To continue practicing ideas of sampling, we will now use a population of baseball players. Our goals for today are to sample from a population using R, to write a function that will sample from that population, and then a function that carries out an estimator. We're going to apply that function to samples that we generate, and then we can see the performance of those samples. In the next video, we'll use this example to connect sampling to the replication crisis in science, and then in the video after that, we'll discuss the future of sampling. So our data today come from baseball salaries. You probably know that some players have extremely high salaries in Major League Baseball. You may not know that the minimum salary in MLB is $720,000 per year. At least that was in 2023. So there's a huge amount of inequality among baseball players. While some players are making $30 or even $40 million a year, some players are stuck with only $720,000. This is a nice example to think a bit about inequality because everyone's actually pretty well off. It's also a nice example because we can work with the entire population. USA Today put together a database of baseball salaries online, which I scraped. This database has all 944 players who were on opening day rosters in 2023. If you go over here to the course website, you can actually download these data by copying this chunk of code to read the baseball data set from our course website. Okay, so a few descriptive facts about this population. Baseball salaries are really high. The mean in this population is almost $5 million. You can also see that there's a long right tail with those few people making about $40 million and then lots of people down here near $720,000. Baseball salaries also differ a lot across teams. So some teams like Oakland have fairly low salaries on average, and some teams like the New York Mets in 2023 had a really high average starting salary. On the course website, we also have a plot where you can see that the average salary teams that are very high also tend to be the same teams that have very high standard deviation of salaries. So the New York Mets pay their players a lot on average, and there's also high variability among the New York Mets. So with this information, you should now conceptualize the sampling strategy. So before you read on the course website, you should think, what would it mean to use each of three possible strategies? A simple random sample of 60 players, a stratified sample by the 30 MLB teams, and a sample clustered by those 30 teams. Okay, you've had a chance to think about it? So a simple random sample here would be 60 players chosen at random. If we want to be technical, these should really be chosen with replacement with equal probabilities independent of one another, but here we're going to imagine taking 60 players without replacement so that no one appears in our data set twice. A stratified sample is a different sampling strategy where we take 2 players on each of the 30 teams. An advantage of stratified sampling is that it guarantees to represent all 30 teams in the sample, and you know their proportions before you ever draw that sample. There's no randomness in whether the Dodgers are included or not. A clustered sample is often used for cost reasons. Under this strategy, we might first sample 3 of the 30 teams, and then on each team, sample 20 players. This is often cost-effective because you only have to talk to the people in the front office of 3 of the teams. The downside of cluster sampling is that it can be higher variance, because if you happen to get the teams that pay their players a lot in your 3 teams, you might way overestimate the population mean salary. Okay, so how would we apply an estimator to these samples? I first want to talk on the course website about how we might draw some samples from the population ourselves, and then we'll talk about how we could apply an estimator to those samples. So in code, what would it look like to take that simple random sample? I'm going to make this a little larger, actually. Okay, so here I've written a function that draws a simple random sample. We begin with a population. This is going to be our data set of all the baseball players. We take that population and we pass it down to a mutate function. This step is going to be a little complicated in each example. Here I'm creating the probability of sampling. We're going to draw 60 people divided by the total number in the population. And so the sampling weight on each person is going to be 1 divided by the probability that that player is sampled. Then here I'm using sample n to sample 60 players. So here we say we have this big data frame, and sample n tells R, please take a random sample of size 60. So when we call this function, we pass our population data frame into the function, and we get out a data frame of a sample with 60 players. Now in a stratified sample, we sample 2 players on each of 30 teams. So to do that, we might first take our population and group it by team. Remember, when we group by, then R uses the groups for all the subsequent operations until you tell it otherwise. So within the groups defined by teams, we're now going to define the probability of sampling. Each player's probability within the team is 2 divided by the number of players on the team. Here I've omitted the probability that their team is selected because we always select all of the teams. The sampling weight is the inverse probability of sample inclusion, and then we draw our sample. So because we're grouped by team, we're going to sample 2 players per team. A clustered sample is a bit more complicated. So in a clustered sample, we first are going to select the teams. Here I've taken the whole population of players, and distinct is going to reduce the data set to one that only has a column for team and 1 row per team. Here we're going to sample 3 of those teams and then store them in a vector. So pull takes a variable out of a data frame and hands it back in a vector form. Here I'm taking all the players and I'm going to look at those who are in the sampled teams. Then within those teams I create sampling weights and I sample 20 players per team. So you can go ahead and play with these estimators. You can copy each chunk of code, and you can take your own clustered sample, stratified sample, and simple random sample from the population. With those samples, we then would want to use an estimator. So we've all learned to use weighted means in this class so far. Here I'm going to talk about wrapping those means in a function that carries out the whole estimation task. I like to call this function estimator because it takes a data set and it returns an estimate. So here I'm writing a function where the argument to the function is going to be a tibble, which is a sample taken here from our population. The function is going to take that sample and then summarize that sample with the weighted mean, the mean of salary weighted by the sampling weight. And then it's going to return the estimate. The reason I like doing it this way is because it's really clear that an estimator is a deterministic function. We take an input sample and we return an estimate. This becomes a useful tool when you want to use computational tools to estimate the uncertainty of your estimator by resampling, or in other cases where you just want to really be clear about what's going on where the sample translates to an estimate. Finally, in this example, we can actually draw many samples because we have the population. And so in R, we can have it run this many times. Here I'm doing that with the replicate function. So I'm calling replicate and telling it I want to replicate this action 1,000 times. What's the action I want to replicate? I have an expression here. The expression is what R is going to do each time on every replication. So it's going to draw a sample, which in this example is a simple random sample from my population, and it's going to return the result of applying the estimator to the sample. So I do this 1,000 times, and I can get a distribution of estimates. And here's that distribution across our 3 sampling strategies. We see that for all 3 sampling strategies, the estimate, which is based on a weighted mean within the sample, is centered on the true population mean, represented by the vertical bar. That's the true average salary of all the MLB players. Now in each sample, we might be a little higher or a little lower than that true mean, and that's what's represented by these histograms here. You'll notice that the histograms are approximately normally distributed, and that's by the central limit theorem. You'll also notice that they have different spreads. So here the most notable result is that the clustered sample is much more variable than the other 2 sampling strategies. This is because if you happen to get a sample that has the New York Mets and the New York Yankees and the LA Dodgers, then you're going to estimate a really high estimate. And that would almost never happen by random chance if you took a simple random sample. The stratified sample has some advantages over simple random sampling, especially because teams are so different in their average pay and their variance of pay. But in this case, it doesn't make a huge difference because those are 2 similar distributions. In general, there are some cases where a stratified random sample may be much more efficient than a simple random sample. So that's how to draw a sample from this population of baseball players and how to think about its performance for estimating the population mean. In the next video, we'll talk about the dangers of working with only one sample, which in practice is what always happens because very rarely do we really have the population.